Let's start now with the halogenation of benzene. Benzene can react with an halogen, and here we will start with the so-called bromination. The mechanism of the halogenation is a normal electrophilic substitution reaction mechanism, but we have to do an additional first step in which the halogen reacts with the Lewis acid in order to form a powerful electrophile. And the reason for this is that bromine is not enough as electrophile, and therefore we always need the presence of a Lewis acid which acts as catalyst. And as Lewis acid we can, for example, as here, use the iron tribromide, or we could also use aluminum trichloride. In the first step, the bromine approaches the Lewis acid as the Lewis acid enhances the electron withdrawing effect of one of the bromides. So in the first step, the Lewis acid will accept a pair of electrons from the bromine, and then we end up with a so-called coordination complex where we have one partially positively charged bromine atom. This coordination complex is now a much stronger electrophile, and therefore benzene will now act as nucleophile and the electrophilic substitution reaction will proceed. Here, one of the double bonds of the benzene molecule will attack the partially positively charged bromine atom in this coordination complex. And then in this second, so slow step, we produce a non-aromatic carbocation. And this step is slow as we break the aromaticity of benzene. And also important to see is that we now just draw one molecule for this non-aromatic carbocation, but be aware that you have resonance structures. So this is not the only structure you could have. And then we have a third fast step where we have a deprotonation step of this carbocation in order to regenerate the aromaticity, and then we finally end up with this bromobenzene molecule, which is now a substituted benzene molecule, where we exchanged one hydrogen atom with bromine. Additionally, we generate hydrogen bromine, and we regenerate our Lewis acid. So the bromination of benzene is always a Lewis acid catalyzed reaction, and the mechanism is an electrophilic substitution reaction mechanism. The chlorination of benzene proceeds very similar to the bromination, and this electrophilic substitution reaction is again Lewis acid catalyzed. Exactly as for the bromination, we start with the first step where we have to generate a more powerful electrophile. Therefore, the chlorine will react with our Lewis acid catalyst, which is here the aluminum trichloride. And then we form again this coordination complex, which is a powerful electrophile, and we start the electrophilic substitution reaction then with the attack of benzene, which acts as nucleophile on the positively charged chlorine. In this way, we form a non-aromatic carbocation, and again, be aware of that you have resonance forms of this carbocation. And the last fast step is again the deprotonation of this carbocation, and the driving force is the regeneration of their aromaticity. We end up with this chlorobenzene molecule. Again, one hydrogen atom of the benzene molecule is here substituted with one chlorine, and additionally we generate hydrogen chloride as well as we regenerate our Lewis acid, which acts as catalyst. So also the chlorination of benzene is a Lewis acid catalyzed electrophilic substitution reaction. So now we had the bromination and the chlorination, which are Lewis acid catalyzed electrophilic substitution reactions, and now you might think we could do the same reaction mechanism with other halogens, but this is not the case. So for the fluorination, we have the problem that fluorine reacts extremely rapid, and it is very difficult to control the number of fluorine atoms which are introduced. In contrast to the fluorination, if we want to use iodine, then we have the problem that iodine does not react at all with benzene. And In order to form iodine benzene out of benzene and iodine, we need an oxidizing agent, such as nitric acid, in order to form two iodine cations, which are then strong enough electrophiles to react with benzene in an electrophilic substitution reaction.